This presentation is on autoencoder-based semantic communications, and my name is Professor Anil Fernando, Professor in Video Processing and Communications here at Computer Science Department in the University of Strathclyde in Glasgow. So my main research work is concentrated on video processing and communications for different applications, machine learning, and recently we started some work on semantic communications for emerging applications like 6G and machine-to-machine communication and machine-to-human communication. So this presentation is all about how semantic communications can be used in machine-to-machine communications of understanding images. So first of all, we will introduce some of the concepts on machine autoencoders. And autoencoders is a type of an artificial neural network. And this has two components, an encoder and the decoder. An encoder is doing the encoding function that transforms the input data to a reduced dimension vector space called the latent vector. And latent vector is used by the decoder who transforms the latent vector to recreate the input data from the encoded representation. So this is a typical architecture of an autoencoder. So we have X input image, and then it encodes, like I mentioned before, to reduce dimensions for the latent representation. Here I denote it as H. And we have a decoder to use this latent representation vector H to reproduce an image which is something similar to the original image. So encoder is kind of acting as a compression module to compress the input data to a latent vector space, usually a very small dimension compared to original size. And we denote H is a function of X because H is completely depending on the input image X. So the decoder does the opposite operation. It tries to reconstruct the output image from the latent vector H. So therefore, R is the decoded output. R is a function of G of fx with R close to X as much as possible in doing this encoding and decoding process. So what is an autoencoder? It's a kind of an unsupervised neural network, like I mentioned before, that tries to reconstruct the output layer as similar as the input layer. So starting with the image X from the input side, I start to reduce it to a latent vector space called Z here, and then Z is expanded at the decoder side to regenerate the an image called X dash, which is quite similar to the input image X. So encoder is a mapping function from the input space to a lower dimension space, and decoder does the reverse operation by reconstructing from the lower dimension space to a outer space, or output space. So there are three types of autoencoders you will find in applications so far. So the first one is called the regularized autoencoders. So this is the most common type of autoencoders available in the literature, mainly for like the denoising applications and sparse applications. So the second one is the concrete autoencoders. So they are mainly designed for discrete feature selection. A concrete autoencoder forces the latent space to consist only of a user-specified number of features. User has much more control on these kind of autoencoders. Finally, there is another one type of autoencoders called variational autoencoders. So this is mainly like for with different goals and with completely a different mathematical formulation. So latent vector is in this case is in case composed of a matrix mixture of a distribution of instead of a fixed vector. So out of these, regularized autoencoders have been widely used as of today for different applications. So what are the applications of autoencoders? Mainly for image compression, image search, image denoising, image generation, sequence prediction, and anomaly detection. So all these applications are the typical use cases for autoencoders. So what is the motivation here for us in this talk is to use the autoencoders for solving a communication model problem. So this one is a typical communication model where we have the information source and the transmitter. So information source is mapped to the input to the transmitter. Transmitter generates the signal, and then it's transmitted through a noisy channel. And then at the receiver, we have the receiver, and the receiver regenerates the message and put it into the destination mode where it can be used for different applications. So it's a typical communication model, like we find in most of the communication applications. So the motivation here is related to the Shannon capacity limit theorem. So Shannon has defined the channel capacity is a function of B. B is the bandwidth and signal noise ratio of the channel. And C is equal to B of log of 2, 1 plus S over N, where C is the channel capacity, B is the bandwidth of the channel, and C S over N is the signal noise ratio of the channel. So basically, you can control channel capacity by increasing the bandwidth and increasing the signal noise ratio. This was proposed about 7 years ago, and people have been using this for over the years for different communication applications. So what we are trying to do is, so even though Shannon has defined this channel capacity, and recently people have shown interest on the second layer of the semantic pyramid, which is the semantic meaning of the image, so the information. And if you can exploit the semantic meaning of the information, and then we can say that theoretically, we can beat this channel capacity theorem by sending the information across the channel and also by sharing some of the knowledge between the receiver and the transmitter, which is known as the semantic information. And this is our agenda for today's talk and how autoencoders can be used for this purpose. So the objectives of this presentation is to get some familiarization of implementation of autoencoders for semantic communication and transmitting images over an phone channels, and train the autoencoders on different channel conditions, and implement an end-to-end autoencoder-based semantic communications for image transmission, especially for machine-to-machine application, and semantic-based image transmission of performance evaluations under different channel conditions. And finally, to implement a CNN model for understanding these images, which has been transmitted over the noisy channels using autoencoder-based semantic communication system. And this is the proposed autoencoder-based system for machine-to-machine applications. And we have the input image, and which is encoded using an autoencoder. And then we have the channel encoder. In this case, we have used a polar encoder to protect the data. And then we have a modulation scheme. In this case, we have used the binary phase shift keying as the modulation scheme. And then after the modulation, we put them into the channel, and channel will introduce some noise. And then at the receiver side, we use the BPSK or binary phase shift keying demodulator and polar decoder. And then take the output from the polar decoder and put it into the auto decoder-based autoencoder to regenerate the received image. So once we regenerate the image, so this will be applied to a CNN image classifier to understand what is inside the image. This is mainly done for machine-to-machine application demonstration scenario. And this is the proposed autoencoder architecture. You have the input image, and then we are using 2 convolutional layers, one with 28 by 28 by 32, and then we are using max pooling in between before we start the second convolution layer. So after the second convolution layer, we tracking the data to generate 3,136 data points, and then we use one dense activation of 32 data points with random activation function. And this is the reverse operation of the autoencoder decoder. I start with latent vector of 32 by 1, and then we generate the dense layer with radio activation function of 3136, and then 2 deconvolutional decoders and to regenerate the output image. And this is the CNN image classifier. We again use 2 convolutional layers followed by 3 dense layers, hidden layers to get the output from the CNN classifier. And for the test setup, we used a means dataset with 20 training images and 10,000 testing images, each of which has 784 by 1 pixel in size. And the big bits per pixel is 8 bits. And that means the pixel values is changed from 0 to 55. And with different noise levels, random noises have been added to the 20,000 dataset to create a new dataset of 20,000 training image sets. And these are the results. And basically what we have done is we have trained the autoencoder and decoder under no noise and under different noise levels. So this graph represents how the PSNR or the image quality is changed between the channel signal to noise ratio. And you can see that the decoder with zero noise as the training data and is underperform all the other techniques, all the other auto encoder decoders with a significant margin at mid-range signal noise ratios and at highest NRs. So zero training one gives the best results, whereas the other trained decoders perform slightly lower than the zero error one. So these are the observation quality of the received images for different channel SNRs considered. Autoencoder is trained with no noise and different noise levels. PSNR is saturated over 3.5. At lowest NR, everything is getting a poor quality. Obviously, when the channel SNR drops below a certain threshold level, so the performance can't be maintained like in other communication system. But interested in the mid-channel SNR, autoencoder trained with different channel errors recorded the best image quality. And this is how the PSNR is varied across the different channel bit error rates. So again, autoencoder trained with 0 bit errors recorded the worst performance across high bit error rates, but at 0 bit error rate, it gives the best performance. And here are the observations for that particular scenario. The third one is we try to test how these images, received images, can be perceived by the machines. So for that, we have used a CNN architecture that I proposed before as to understand how machines can understand these images. So on the y-axis, we have the accuracy, percentage of accuracy for different decoder types. A decoder trained with 0 bit rates again failed to achieve a high accuracy in the middle range of SNRs, but at high SNRs, all decoders trained with 0 and higher bit rates gives a similar performance for the accuracy. And this is again how the accuracy is changed with the bit error rates, like in the previous case. Higher the bit error rates, the auto decoder trained with 0 bit errors gives much lower performance compared to the other decoders. So finally, we have considered the impact of scheme on actual communication systems, and we used an equivalent JPEG video transmission system as the baseline. So with the proposed architecture, we could compress the image approximately 40 times compared to the original image size, and computational cost is slightly higher than the JPEG. But when the JPEG transmission system is considered, proposed system managed to compress the image approximately 40 times, like I mentioned before. Minimum JPEG compression we could achieve was approximately 15 times compared to the original image, because we could not reduce the JPEG compression below that point to regenerate the recorded output. Since JPEG has the lowest coding performance threshold, beyond that we cannot compress any images using JPEG beyond that point. Basically, we have achieved that the lowest level compression capacity of the JPEG encoding. So at high signal to noise ratios, 3.5 dB or higher, JPEG compressed images recorded higher PSNR because it has the best capacity of increasing the quality, but at a much higher compression, much lower compression efficiency. So at 3 dB and below, JPEG failed to transmit images under similar constraints. So basically, our proposed architecture based on autoencoders gives better best performance at mid-range of SNRs and the low SNRs. Because JPEG failed to receive the images at noisy channels. So what are the conclusions? The conclusion is semantic communication enabled autoencoder-based image transfer system is proposed. So we have proposed an autoencoder-based transmission system, and once we train the encoder and the decoder back to back, what we have done is we have detached the encoder and decoder, and we use the encoder at the transmitter side, and then decoder at the receiver side, and then these are separated by a traditional communication channel with other communication components like the channel encoder and the modulator in between, and the channel decoder and the channel demodulator at the receiver side. So we have like developed an end-to-end system. Once it is trained, during the training process, semantic information is extracted. And once that is trained, so we detach the encoder and decoder, and then put one into the encoder, the transmitter side, one into the receiver side. So autoencoders under different channel SNRs are trained and evaluated. So we have used different channel SNRs to train autoencoders and decoders. And we have used these trained networks for different scenarios, and then we tested the results under different channel conditions. So all encoders recorded similar performance irrespective of their training for all bit error rates. So at highest NR or low bit error rates, the codecs performs much better performance. But when you go towards the lower bit error rate, high bit error rates, autoencoder trained with zero noise have failed compared to the other decoders. So what is the future work? So since this is already implemented and we could extend this for different applications. So one of the future work that we can concentrate on extending this work is for semantic communication enabled hybrid image coding for noisy channels. What it does means also in this presentation, I only talked about the machine-to-machine communications where one machine sends the information and the other machine receives the information and understand the content of the image. Whereas this can also be extended for a human application like machine-to-human applications or human-to-machine applications, where the processing of the information and presenting the information could be slightly different. For example, in this scenario, this one can be easily extended for machine to machine. This is what we have proposed here. And then also machine to human applications. For humans, you need better quality than the machines. So therefore, we need to enhance the image quality subjectively or objectively much more higher than what the machine could perceive these images. So for that, we have to send some other additional information across the channel to increase the human perception. And that's one area that we can extend this work in the future. The second one is, of course, the interesting area to work on this for scalable image transmission over Europhone channels. So what it does is, so like in the scalable image coding and transmission using JPEG, the proposed system can also be extended for scalable image transmission. What it could do is, so the base layer can be extracted from the autoencoders, and then we can generate a series of enhancement layers, and these enhancement layers either could be encoded using autoencoders or any other traditional ways of encoding the residual images. So, and the receiver, so you can recombine these base layers and residual layers to enhance uh, the quality of the images based on the scenarios of where the users are and what kind of resources they could get from the communication system. For example, if somebody is having uh, uh, difficulties of receiving the signal, so they could go for like only for the base layer and drop in this enhancement layers. Or if somebody is very close to the mobile station and have a very high battery power, so then they can he or she can download all the enhancement layers and the base layer to enhance the perception of the image. And finally, this could also be extended, like I mentioned before, for hybrid machine-to-machine and machine-to-human communications. So machine perception enable autoencoder-based image transmission. So what it could mean is, so right now we are using like conventional image quality metric like PSNR or SSIM or any other kind of mathematical model which could be used for human image uh, applications, but these are not ideal for machines. So machines understand the images or video in a different perspective compared to the human. So therefore, one needs to develop some machine perception quality metrics to understand the transmitted received image, and based on that, this whole end-to-end chain can be further optimized, especially like if we are using autoencoders for transmission and receiving. So these encoders and decoders can be trained back to back based on the machine perception metric rather than the human perception metric. So this is another area that we can work on in the future based on these autoencoders. And finally, this can also be extended for video coding, where autoencoders can be used to predict the images at the receiving side. So thereby you can start a kind of a new research areas in video coding using autoencoders for different applications. I think these are the main future directions. Immediately, one could consider using autoencoder-based system for semantic communication-based applications in image and video transmission. I think that's it for this presentation, and I hope you have learned something on autoencoder-based semantic communication for image transmission, and hope to see you in the future with a different research area in this domain. Thank you very much.